Hey, hello all. Welcome to another Data Science with Julia video. So today I think we are going to see about linear regression with gradient descent. So last time you saw guessing a number with gradient descent and all those stuff. I don't know why my kernel is not starting. One second, right? Okay, k means okay. This is starting linear regression. Okay, yeah, it started. Okay, fine. So, last time we just saw guessing a number with gradient descent, which is very simple, like 10 or 12 lines of code, we were able to do it. So, today we are going to do linear regression. Last time we guessed a constant, but today, let me just show you what. Okay, so over here, okay, linear regression, okay, right? So imagine like you're given some data points, like some points where there is some features and other points where this features make some prediction. Okay, so that is the x column is numerical value, that is the features is numerical value, and the prediction thing also is also numerical value. You just plot it and you just see like, okay, this might be correlated linearly. So you just have an idea. Okay, let me make this bigger. So it could be something like y is equal to mx plus c, right? Okay, so that's the thing. So what I'm just doing is like right now, I'm just trying to partially differentiate this y with m. Okay, why I'm doing that is okay. I want to find the gradient. Okay, we want to find the error gradient, and this equation will be useful then, right? So when I partially differentiate with m, the c is constant, so it just goes off. So this dou by dou m of mx plus c, that is this xi is nothing but okay. You will be having like thousands of points. So one of the point is I like x1, x2, x3. So the I represents 1, 2, and 3. So for every prediction you make, okay, so when you take the gradient, this m goes off and there's only x, okay, so it equals to xi. And similarly for c, this mx will be should be considered as a constant because it's a partial differentiation, right? So and c should be considered as a variable. So dou by dou c of c is 1. So that's the thing. So, okay, yeah, now I'm just going into the mathematics. So, bear it, but even if you don't understand it, I hope you can get it in programming. Okay, so that's the thing. So, once we differentiate, we find okay, okay, forget about the differentiation now. Okay, so let's go into the error. Okay, so for each and every prediction you make for ith point, okay, so let's say let me try to explain a bit better. Okay, so let me say okay, x is 1 and y is 5. Okay, so and you just make some prediction. You just make some prediction of 3. Okay, so the prediction is 3 and this is 5 for x is equal to 1. So the error will be minus 2. And it's better to get error square. Okay, so we are just taking the error square, possibly because of the absolute thing will take place, but I'm not really sure okay, why we are taking, but this is how the gradient descent works. Okay, that is with linear regression works. Okay, so we are just taking the square of error, right? And then what we do is this is for 1 point. So for total points, like we just do I is equal to 1 to n, whatever the prediction you just make for this I, and whatever is the given value for this I, you just sum it up, sum all these errors up. Okay, so that's the thing. And the average error is nothing but we just divide it by 1 by n. So this is the average error we are going to use. For convenience sake, I don't want to write EAVG, so or square, E square of AVG. So I'm just putting it as E. So that's the thing, right? But it's actually square error. It's actually square average error. So that's the thing, right? Okay, so we just have it. So we just divide this by 1 by n. Okay, so now we do this differentiation, do E by do M. So now these things will come useful, like do y hat I by do M. So we're having it, right? So those things will come useful. So when we do the differentiation, we just get, okay, 2 by n, okay, this equation y hat I minus yi by dou m of y hat I minus yi. So this is actually 0. That is dou by dou m of this one is 0. So that's the thing. So finally we just get this dou by dou m of y hat I. And we know this dou by dou m of y hat I is nothing but xi. So this is it. So what we are just doing, so this is the gradient. Okay, so the gradient of the error. Okay, last time also in this video we just saw, right, like over here in guessing the number. Actually, the error is either positive or negative, and this positivity or negativity is the gradient. Okay, and as well as and this is the number is the magnitude, and with that we were able to get this guess nearer and nearer to this 42 or whatever number you would have put in your Jupyter lab or Jupyter notebook. Okay, so that's the thing. Similarly, this is for a line, and we are also trying to find the gradient, nothing else. Okay, so that's the thing. And now, what will be the m? So it'll very similar to last time. Okay, in the intuition we saw. So the new value of m is something going to be like new value of guess. So guess is equal to guess minus alpha multiplied by error, and similarly that is the error is gives the gradient and magnitude in this case. Over here, yeah, like you just differentiate it and get it. Okay, so this is the formula. Okay, so that's the thing, right? And similarly for C, if you do the same procedure, what you'll get is like what to say, like alpha dou E by dou C. What is dou E by dou C? And dou E by dou C is nothing but y hat I minus y hat. Okay, so you don't have the multiplication xi. Okay, so that's the thing. If you want, you can do the math and see, right? So this is it. If you don't understand, yeah, don't worry much. Okay, so let me show you to you in code, and that's the thing. So yeah, so these are the two formulas you need to kind of remember if you want to do something from scratch on your own or something like that. Okay, so let's go to the code and see how it works. Okay, so uh, okay, where's the code? Yeah, here's the code. Right. Okay. So first, what I do is like I just have a line like mx and c. So that's what defines the line, right? So mx plus c, that's the line. Okay. So I'm just testing line of 2, 5, 3. So m is 2, x is 5, c is 3, and it gives 13. Okay, fine, not a problem. So now what I just do is I just don't want to put. Okay, I just for generation of data first. In order to learn, we need to generate data, right? Of course, I could have taken some data from somewhere and done it, but this is more. If you're learning, it's better to do more. It's better to be more controlled. So to keep the unknown stuff very little, so that you can just understand the concepts, right? So I just want to construct a line y of x is equal to 2x plus 3. So what I just do is like I just put y of x is equal to line of 2 comma x comma 3. So that's the thing. So as simple as that. Now if I put y of I, it's 13. Okay, so now I just take x is okay. These are all the training input. Okay, in real machine learning things, you will separate the training and what to say, the testing and all those stuff. But yeah, this is introduction to data science book. So mostly you'll be learning how the inner workings of machine learning, data science, and why you do what you do, and not like very practicality or something like that. Okay, so that's the thing. So x is equal to 1 to 10. I'm just taking this is a range. Okay, so and y I'm just generating y dot of x. So it'll take each element of x and apply this y thing over here. That is over here. This y thing will be applied over here, right? And you will just get x and y's. Okay, so now I'm just writing an error function. So given that x array and y array and m and c, that is, let's say like m and c are some wild guesses and some wild predictions. Okay, it'll give out the errors. Okay, so what I'm just doing is like first I'm just putting m, 4 and 5. Alpha I'm just defining it over here, but don't worry about that. Okay, m is 4 and 5. Okay, and then I'm just computing the errors. So errors will come out as this one. Okay, so this error is nothing but like you see, right? Where to go, yeah. So it's something like, okay, this one, like e of I. So all the e of i's we are just getting as an array. Okay, so all we need to do is to square it and then minus it and all those stuff. Okay, so I'm just getting the errors. Okay, so now I'm just taking this n as length of y, because like the number of data points, right? It should be like x and y should be equal. Like you can't have like 10 training inputs and 5 outputs. Okay, so that's not the case. Okay, every training input, every training input data points should have a output data point. Okay, so that's the thing. Okay, so now let me just apply this formula. M is equal to m minus 2 by n. So if you look at the equation, it'll hug very closely, right? So it's 2 by where is it, where is it, where is it, yeah, m minus alpha dou e by, okay, dou m. So dou e by dou m starts by 2 by n, and I think I should multiply alpha somewhere. Yeah, alpha is also there. So this thing is completed. So 2 by n is there, alpha is there. Okay, right? And now I just need to do summation of errors multiplied by xi. Okay, so that's what I'm just doing. Okay, so summation of errors multiplied by xi. So I'm just doing element wise multiplication. So this is the thing. Okay, so the m what we assumed was 4, now it's 3.824. This is the kind of m. Okay, like we, y is nothing but 2x plus 3, right? 3.8 is more closer to 2 than what to say 4. Okay, so that's the thing. And similarly for c we are doing, look, once again I'm putting m is 4 and c is 5 because look, m has changed, so I don't want m to be 3.824. Okay, so like it should be 4, and with 4 and c5, what will be the change in c, right? So that's the thing. So it is like 4.974. So 4.974 is more nearer to 3 than 5. Okay, so looks like, okay, we are slowly going to this m is equal to 2 and c is equal to 3. Okay, so similarly, once again I'm just doing with this new values, like m is 3.824 and 4.974. Now m changes to 3.6. Yeah, we are moving towards 2, and this one changes to 4.94. I think we are moving towards 3. Okay, so now let me keep some other values. Okay, m is 5 and c is 0, alpha is 0.01, and let me do it for 1000 times. Okay, so that's the thing. I'm just doing it for 1000 times, and look, m is 2 point something, and c is almost 2.95. That is almost 3. Okay, so I think we have got it. Okay, so what I just need to do is I need to plot it. So I think I need to restart kernel and run all cells. Okay, so that you will get the plot. Okay, so okay, it's restarted. It'll run all things fast, but I think it'll take time in plots. Otherwise, it's not running. Okay, 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 fine, fine, fine. It's running for some. Okay, right, yeah. Now it'll just plot. Okay, right. So what I'm just doing is like, yeah, I'm just doing a scatter plot of x and y. So those will just give the x and y points. Okay, and now I just want to plot this line. Okay, so and see what is the fit and all those stuff. Why it's taking so long? Okay, yeah, fine. Look at the fit. It's almost perfect. But yeah, we don't know it's not perfect because what to say, like it is like 2.0071 in the very, very, very long run, like for very, very high values. Possibly 10,000 or 20,000. Yeah, there might be some deviation, but the thing is like, look, we have some points and it's fitting. Okay. And let's change some values and rerun it. Okay, let me give it like, okay, 10 and 7 just to prove that. Okay, look, still this one works. Okay, kernel, so m should be guessed near 7 and c should be guessed near 10. Okay, restart kernel and run all cells, right? Just to show you. Okay, this is not some kind of sorcery or something like that, and it does work. Okay, so that's the thing. Before, my Apple M1 used to work fast. Now it's becoming slow. I don't know why. So possibly something, the computers got old in just 6 months, and I spent so much for it. Yeah, yeah. So you just got like almost 7.0 something, 02 and 9.85. So it's almost 10 and it's almost 7. So from 0 it has rose up to 10. And look at the fit. Yeah, the fit is good. Yeah. So here is 20, I think here is 10 and something like that, and the fit is still good. So So yeah, this is how linear regression with gradient descent works. And I just want to finish by telling a general formula. Like, look, this you have just done for mx plus c, right? In reality, you will be having a lot of features. Like a table would have been given to you, or a CSV would have been given to you, where you have this feature one, feature two, feature three, and similar to feature j and to feature m, and there'll be m features and one prediction. Okay, and you would be having like n rows. Okay, so for I'm just representing them as xij, that is like x of row comma column. Okay, so that's what I'm just doing, and the prediction is yi. So for each and every row you'll have one prediction. So this is the hypothesis equation. So this time, like, you just had like mx plus c, so now it's becoming like hypothesis is equal to c plus j is equal to 1 to m, aj xi. Aj is nothing but the constants. Okay, so like a1 x1 plus a2 x2 a3 x3 and so on and so forth. Okay, so till am xm. Okay, so that's the thing. And for each and every prediction you make, let's make it like y hat of I, and it is like c plus sigma of 1 j is 1 to m, and what to say, aj xij, because the ith row, right? So that's the thing, and we need to determine these AJs. So that's the thing, right? I think this should be d y hat I of daj. Okay, I just found that mistake. Yeah, I need to change that. So it's going to be xij, and similarly, this should be dy hat I of dc. So it should be 1. Okay, so that's the thing. So this is the error. So like similar thing, 1 by n, the total average, the square of error square average. Okay, so like it should be 1 by n, and what to say, sigma of 1 to n, and the prediction minus whatever the value we have received. Okay, so if you differentiate it, okay, de by daj, we are getting it like this one, like de by daj, that is like it's been multiplied by xij. Okay, so the jth input should be multiplied with it. Jth input of that row. Okay, of that ith row, the jth input should be multiplied to get de by daj, right? Similarly, de by dc, yeah, you can just drop this stuff off, and it's just what to say, the sum of errors multiplied by 2 by n, right? So this is the new updated aj value. So I'm sorry, right? So this is the new updated aj value. So you need to substitute this one, right? And similarly, this is the newly updated C value. You need to substitute. I'm sorry, I don't know. Something has gone into my throat. Okay. You need to substitute this one, right? So that is the thing. So for almost any linear equation, you can just do it. Similarly, you can do it even for quadratic and all those stuff. All you just need to do is to find the derivative and all those things. So yeah, like differentiation and integral calculus are quite important for what to say, neural networks. So if you're a person who's not learning mathematics but just want to become a data scientist, please try to learn mathematics. I don't see it as difficult. You just need to understand it. And what to say, like, yeah, please do learn it. It is very, very important for data science. Like, uh, otherwise, if you're not learning mathematics, you'll just become a data worker. You'll just receive some data and you'll just what to say, feel like if I do if I do this procedure, that procedure, and all those stuff, somehow I get the output. But for in real cases, sometimes that might not work out. So please learn mathematics, right? Anyway, yeah, thanks for watching this video. Do like and subscribe data making if you like it. We are committed to produce more videos and in data science and as well as in many other topics. Okay. Thanks a lot. Do support us. Bye.